that was the first chance I had to see this magnificent valley. As I said, deeper than the Grand Canyon, brilliantly illuminated by the sun, more brilliantly even than a desert sun that I was used to out in New Mexico. And also, but placed against a blacker than black sky. That, I think, was the hardest thing to get used to. Because here on Earth, when you have a brilliant sun, you have a blue sky. Well, the sky around the moon was black. Because of the brilliance of the sun and the illumination on the mountains, your eyes couldn't adjust to see stars. So it was a nighttime sky without stars that was behind an image of a brilliantly illuminated mountain and valley scene. It was really quite spectacular.
You are about to embark upon the Great Crusade
to meet this mounting aggression.
And make no mistake about it, good will prevail.
I was born in a small mining town in southern New Mexico called Santa Rita. It's the location of a large copper mine. My father was a geologist, my mother a teacher at the university, or college then, in Silver City, New Mexico, and that's where I grew up, was in Silver City.
So the desire to pursue studies in geology came pretty naturally.
Well, it sort of happened slowly, but nevertheless, as my father's field assistant when I was in high school and actually even in junior high school, I was exposed to it for a long time. When I was admitted as a student at Caltech, though, I thought I was going to be the world's greatest physicist. But I found out very quickly that in the class, the world's greatest physicists of the future were sitting on my right and on my left, and not in my chair. So I began to move towards geology at that time.
And you received your doctorate in it as well, correct?
I did, from Harvard University in 1964. NASA just asked for volunteers. And in November of 1964, this notice appeared on a bulletin board where I was working, which was with the U.S. Geological Survey in Flagstaff, Arizona, where Gene Shoemaker had established what was called then the branch of astrogeology. He was very, very interested in that field, and so I contacted him, and he contacted me almost simultaneously. And I went to work for him. But in November of that same year, 1964, NASA did ask for volunteers from the scientific community and engineering community for the first group of what were called scientist astronauts. Well, when I arrived, the branch of astrogeology was just forming up, and so I had several opportunities to take on particular tasks. And the one I picked was called Lunar Field Geological Methods, which NASA was funding with Shoemaker's group. And we began probably the first, in fact, I'm sure, the first real concentrated effort to figure out how in the world are astronauts going to be able to do geology on the moon, field geology. And that was very exciting. And then this announcement appeared on the board. And first of all, I asked Shoemaker if it was okay if I sort of broke my commitment to him, and he said, "Sure, I'll fire you if you don't." And so I raised my hand and volunteered very quickly for the program. Actually, the first thing I had to do was prove that I could learn to fly a T-38 aircraft, and the first year as an astronaut was actually in pilot training with the Air Force. I learned to fly T-38s, and a couple of years later, actually learned to fly helicopters. Which were always very exciting and very important, actually, to becoming an operating astronaut. Psychologically, these aircraft teach you two things. One is they teach you to be responsible for any problems that may develop in a mechanical system. And secondly, you can't reset it. It's a simulator that keeps going. Whereas when you train as an astronaut, you spend most of your time in simulators, and if you make a mistake, well, we'll just punch it and start it over again. But you can't do that in a T-38. And our boss, Deke Slayton, made that point many, many times, and I think he's absolutely right. It was important, and I think every astronaut should be a qualified jet pilot, and if possible, a helicopter pilot. The other thing this does is it makes the next thing you start to learn easier because you've got this new experience behind you. So it's very important. I won't say it came naturally. You got to remember, I was 29 when I started to learn to fly aircraft, and normally that starts when people are 19, not 29. And so in that 10-year period, human beings develop a lot of habits and ways of doing things, that some of which you have to unlearn in order to be a good pilot. I think I did that. I think I was a very good pilot, but nevertheless you have to do that. And so it's not a natural process, it's a learning process.
Was the results you got from Surveyor what you expected it to be based on your expertise?
Yes. Again, the famous planetologist Shoemaker and I had talked a lot about that before Surveyor landed. That was happening in the same part of the time that I was at the survey office in Flagstaff. That was one of the possibilities for my work, was to join the Surveyor team. But we did talk about it and tried to make our own predictions of what it would be. And from a geological point of view, even in those days, the best prediction was that it would be a very well-packed surface because of the impact of other meteorites. It's like tamping sand before you pour concrete on it. You do that, and the moon is tamped continuously by these small, what we call micrometeorites. And so it was not a surprise when Surveyor landed very safely, and that the scoop that they had on Surveyor then gave us even more details about the nature of the surface. The main thing I did was, once I was out of pilot training, was that I put together a training program that was based on simulation and also on field work, the combination of using the equipment that they would have on a particular mission and going out into the field on a project or an area that would hopefully have some relevance to what they would see on the moon. But the main thing I wanted was, and that it was agreed that they should do, and I hope the Artemis astronauts will do that as well, is learn some basic principles of how do you approach a scientific problem in the field. What is important, what isn't important, and how do you look at the background at the same time that you're looking at the details that are inconsistent with that background. That's a very important set of principles for field geologists. And so the program we put together, which ultimately I think was very successful, was to bring the astronauts thinking about that. Prior to that, they really had been getting lectures and sort of Geology 1 type training, but they weren't integrating it into what kind of equipment do I have, to sample things, what kind of camera do I have in order to document those samples. And that's what this new program did. And so beginning really with Apollo 12, but mostly with 13 through 17, we had a very systematic program of that kind of training. Actually, each crew training schedule had a week a month in which they were out in the field doing that kind of work. And I think the sample collection that we have from Apollo, some 850 pounds of material that was brought back from those 6 landing missions, is a testimony to the quality of the work that these teams did. I was just happened to be one geologist among a bunch of pilots that had become to some degree geologists. So one thing they couldn't have, of course, is 10 or 15 years experience of having operated in the field, and that's what I brought to the table, as well as we were able to go to a much more complex site on the moon than normally was done in Apollo. The Valley of Taurus Littrow is really a magnificent place to explore.
Now, before your mission, what samples that were brought back from the earlier missions intrigued you the most?
Well, I think that the main thing that intrigued me was their diversity. Much more diverse than one would have had gathered from just the photography that we had from orbit around the moon. The Lunar Orbiter mission took some magnificent pictures of the surface of the moon. We used them for our planning. But I was impressed by and spent a lot of time with the sample collection before I flew I was surprised at the diversity of the rocks that were on the moon. Of course, they were not as diverse as here on Earth, but more so than I had really expected. And when I arrived in the Valley of Taurus Littrow, I found that they're even more diverse than I expected. So it was really an exciting time for a geologist. I think we could apply much of our geological experience to the moon. The one thing that the moon, of course, doesn't have is the effects of water and of air. Geology on the Earth is tremendously affected by the processes that come with water and with moving air. With the moon, of course, it's a hard vacuum, and there's no water running in order to change things. And that's one thing that we didn't have to apply to our knowledge on the moon is the effects of water and air. But once there, particularly in this valley, which was dominated by high mountains on either side, the valley actually was deeper than the Grand Canyon of the Colorado. The mountains on the south went up to over 7,000 feet from the valley floor, and the mountains on the north up to 6,000 feet from the valley floor. So it was a very narrow valley. It was only about 5 miles wide at the point where we landed, and that was one of the narrowest points. So it was spectacular scenery as well as spectacular geology. The decision became public, and we became aware of it, to cancel Apollo 18 in the middle of our training for Apollo 15. Dick Gordon, Vance Brand, and I were the backup crew for Apollo 15. And when we found out that Apollo 18 had been canceled, which normally would have been our cycled mission, we just put that much more effort into trying to make sure that we were competitive for the Apollo 17 mission. When that, in August of 1971, when that decision was announced, and Apollo 15 had landed on the moon about a month before, I received a call from my boss, Deke Slayton, and said, "Would you like to go to the moon?" But later on, I found out what had caused that call to be made. And his original recommendation to NASA headquarters was that the full backup crew from Apollo 14 cycle into Apollo 17, which was the normal thing. But headquarters said that Joe Engle would have to be, either you'll have to replace Joe Engle with Jack Schmitt, or you'll have to replace the whole Apollo 14 backup crew with the backup crew from Apollo 15. Deke had decided that just to replace Joe Engle, and so I was put on the crew for that reason. Headquarters felt very strongly that a qualified pilot, qualified astronaut who was also a geologist should be on the last mission, and that was determined really, I think, primarily by George Lowe, who was deputy administrator at the time. And agreed to, of course, by the administrator, and so I was put on the Apollo 17 crew fairly late in their training, after they had already been training for about 4 months, which was sad. I mean, I realized that it was sad for Joe, but nevertheless, I think obviously think it was the correct decision. We had a wonderful mission, Apollo 17, and in large part, I think, because of the science. The one thing you can't simulate during launch simulations is the vibration that the rocket has when it's starting off. The first stage of the Saturn V rocket developed 7.5 million pounds of thrust, 5 big engines. And that the interaction of the plumes of those engines creates a very heavy, low-frequency vibration in the Saturn V. And that's something that we just never simulated. And in fact, during our simulations, there was a bit of a competition between the crew and the Mission Control Center as to who could figure out what the simulation supervisor had done to make things more difficult for you. What had he failed, and that kind of thing. Well, and so that competition was very fun, and it was based on me being able to see the the dials and operate the switches and things like that. Well, once that I was in the capsule, actually in a launch, that vibration made that front panel vibrate so that I couldn't read it. So I was a passenger, no question about it. Now, had we had to abort, I wouldn't have been a passenger any longer, and you would start to utilize all that experience. But we really, that first stage rocket was something that to behold, not only visually, but to write on. No question about it. My main job as the LMP, the Lunar Module Pilot, was to provide the commander with information about what the status of the spacecraft was. I was basically the systems engineer for the spacecraft, and also what dynamic parameters there were and how they were changing. Really, landing on the moon was a two-person job. Whatever commanders may say that they could have done it without the Lunar Module Pilot, that's not true. Because the Lunar Module Pilot was providing the information the commander needed to know where the what the rates were, where the spacecraft was headed, and then just in the last part of landing, what the altitude rate was and the lateral rates were, so that he could adjust the landing and actually perform the landing. It was clearly a very complicated two-person job. And it got even more complicated in simulations when you started to deal with possible abort situations, where both members of the Lunar Module crew, the Challenger crew in our case, would have to be very, very clever and very, very coordinated in how they flew the spacecraft in those abort situations.
All right, so tell me what it was like to step onto the surface of the moon.
It was a wonderful experience, but for about the first hour, I was doing things very close to the lunar module, to the Challenger, getting equipment out of the bays and things like that. So it was not that much different, really, visually, than being at here back on Earth dealing with your spacecraft in the tests and everything. You were looking at the same kind of equipment, identical equipment. And I didn't really get a chance to take a good look at where I was until the procedures we had developed had me go away from the lunar module, maybe about 50 meters or so, and start to take some panoramas before we really stirred up all the soil around the lunar module and everything. And so when I was taking those panoramas, of course, I was clicking a camera that was mounted on my chest, but I also was looking at that was the first chance I had to see this magnificent valley. As I said, deeper than the Grand Canyon, brilliantly illuminated by the sun, more brilliantly even than a desert sun that I was used to out in New Mexico. And also, but placed against a blacker than black sky. That, I think, was the hardest thing to get used to, because here on Earth, when you have a brilliant sun, you have a blue sky. Well, the sky around the moon was black, and because of the brilliance of the sun and the illumination on the mountains, your eyes couldn't adjust to see stars. So it was a nighttime sky without stars that was behind an image of a brilliantly illuminated mountain and valley scene. It was really quite spectacular, and I was storing all this away every time I went out. I took 3 of those panoramas, and that's really the main image I have in my mind of what I was seeing in general of the Valley of Taurus Littrow. Blue marble photo was taken on the way to the moon. And soon after launch, as a matter of fact, because we were close enough to the Earth in order to see the entire sphere. It was basically a full Earth. But the blue marble photograph I took as part of a long series of photographs that were documenting my weather observations of the Earth. That was one of my major activities I had planned to do. It wasn't in the flight plan, but I planned to do as an amateur meteorologist to look at the weather patterns of the southern hemisphere and how they, not only what they were, but how they developed over the course of 3 days. The Earth, of course, was turning beneath us every 24 hours. We were on our trajectory was actually tied to the moon, so we were seeing the Earth rotate every 24 hours, and I could try to forecast what I would see the next day, and then see if I verified that. And it was really there's pages after pages of transcript of me talking about the weather patterns, the cloud patterns mainly, of what I could see on the Earth during those 3 days going to the moon.
What's it like to know that you took one of the most famous pictures ever?
Well, I didn't realize that until many weeks really after the mission, because it was part of the series of photographs that document weather observations. But it was very gratifying. People have really enjoyed that picture. NASA tells me that it's the most requested photograph from the Apollo archives, and so I'm really very proud of it. And it has some great stuff in it, all of Africa. You can see all of Africa and most of Antarctica, all in one picture. I had a different background than everybody else. It didn't surprise me to see the Earth. I'm a geologist, for crying out loud, and was what I grew up doing, was studying the Earth. And it didn't surprise me that the Earth was out there. And it was another thing to observe, magnificent, beautiful, but it was another thing for a scientist to observe, and I enjoyed doing that, and I think was very successful at it. 76535 is a rock made up of mostly of olivine and a plagioclase and a type of pyroxene called orthopyroxene. And it is one of two rocks, actually, that the evidence now, I believe, says came from deep within the moon. Came from that rock probably from around 400 kilometers down from the surface, and another rock, 72415, which is almost entirely all olivine, that rock came from a deeper point in the moon, probably around 500 kilometers down. Those two rocks are the only ones in the collection that people have recognized so far that have probably come from deep within the moon as a result of a very large impact that occurred about 4.3 billion years ago, called Procalarum. The troctolite is very important. It has helped understand how rocks like that can come from that deep and actually be available to us to sample. You wouldn't normally have expected those rocks from that deep within the moon to be available for collection, but clearly they were, and now you have to explain, why are they there?
How do you calculate how far deep it came from?
Mainly by the assemblages of minerals that are in the rock, and how and the alteration of those minerals due to a pressure change. You see, interestingly enough, I worked on the same kind of problem in Norway as for my doctorate's thesis, and where rocks had been formed at very high pressure deep within the Earth, and then very rapidly brought close to the surface by the tectonic dynamics here on Earth. Well, in the case of the moon, that they were brought up by the impact dynamics, by the release of pressure, and when rocks formed at high pressure are exposed to low pressure, they change. They give evidence of that by how the minerals react. And that's how we can tell how deep they were originally, because you see they partially changed as a result of the pressure release.
I've also heard that, to your surprise, I believe, you found some red dirt on the moon?
It was a surprise, but on the other hand, it helps to illustrate what field geologists do. You always go into the field with as much understanding as you have about the area that you're going to study, and you develop what we call multiple hypotheses on how to explain what may be there or what you know is there. And then you're trying to get new observations to verify one hypothesis versus another. And one of the hypotheses we had for visiting this dark crater called Shorty was that it might be a volcanic crater. And so in the back of my mind, I was thinking volcanism for that crater, even though all the images that we had of it before launch really did point towards it being an impact crater, like almost all other craters are on the moon. So when I walked up to the edge of that crater and saw this orange color in the debris at the rim of the crater, my first thought was, well, it's a volcanic crater, because on Earth you see coloration around volcanic craters. This is the first color we had seen, being in the valley of Taurus Littrow. And so my first thought was, well, maybe it is a volcanic. Well, as soon as I looked at it closely, it was clearly a 100-meter diameter impact crater, another impact crater. But how did it get that red color? And so if you go back into the transcripts for the next half hour as we're driving to some other place on the lunar rover, I'm speculating, taking notes, verbal notes really, that the communication system was my notebook. And normally in the field you have a notebook, you write all this stuff down. But I couldn't do that with the gloves and everything, so I was just recording, dictating notes. I'm going back and forth trying to figure out how in the world do you get volcanic-like color around an impact crater. And well, we didn't know at the time that it turned out that this red or orange soil was indeed volcanic ash that had been deposited about 3.5 billion years ago, and then about 3 million years ago, the crater was formed. Shorty crater was formed and exposed this material, so it was volcanic ash, but it wasn't because it was a volcano right there at Shorty crater. You can see why geologists have so much fun,
Oh,
right?
yeah, I can tell how much you love it now, 51 years later.
I still am very active in lunar research. About half my time I'm trying to synthesize all of the information that has been collected on the samples, as well as what we collected in the field about Apollo 17's landing area.
What's the most significant thing we've learned from the lunar materials?
I think the most significant thing that's been learned is that the moon and the Earth were formed about the same time, 4.5 billion years ago, 4.5 billion years ago. And about the same time as the solar system was forming. And by a very similar process, these two planets, one small, one large, were forming. They are similar in composition, almost identical in most respects, except for water and things like that. And we also now are learning from the examination of the cores that we took. We took what's called a deep core that's about 3 meters deep. And that core is starting to tell us more and more about the history of the sun. Shoemaker always said that the regolith of the moon, that debris layer that covers the moon, is the library of the sun. Because as things accumulated there, it was recording what the sun was doing at that particular time. And we're now getting into that as well. And one of the more interesting things is, one of the changes in the sun that we've been able to decipher now in this deep drill core is a change that occurred probably about 500 million years ago in the energy of the solar wind. The energy of the solar wind appears from the isotopic evidence that we have to have increased by about a factor of 2, maybe a little bit more. And it turns out something was happening on Earth about the same time, and that was what we call the Cambrian explosion of life. That is when the quantity and diversity of life exploded over a few tens of millions of years, about 500 million years ago. And we've always thought here on Earth that, yeah, there probably was an increase in the energy of the oceans. But why did that happen? Well, now we're seeing evidence, the moon's telling us that it happened because the sun changed. The sun became more luminous, and more energy was coming into the Earth's atmosphere, and eventually into the oceans, and that stimulated this explosion of life, of diversity and quantity of life. So you can start to see that we're beginning to tie back. We're not only about the origin of the moon and the Earth, but now about some of the events that were so profound here on Earth that we are the relics of now, namely the diversity of life.
Amazing. Sir, you knew this would be the last mission in the Apollo program. So what was it like getting back onto that lunar module for the last time, knowing that you and Gene Cernan were going to be the last ones, at least for a long time, to set foot there.
Well, I wish we could have had the consumables and everything necessary for a fourth EVA. And Cernan and I talked a little bit in the cabin about where we would go if we had a fourth one, but the consumables weren't there, primarily because we took payload. We took scientific experiments, several hundred pounds of scientific experiments, and had we not taken those and just had oxygen and water in the spacecraft, we could have stayed another day. The lunar module, the Grumman Aircraft Corporation that built the lunar module really did a fantastic job, and their early predictions were that we would have a lunar module that could spend 4 days on the moon. And eventually, with modifications and everything and growth, that's what we ended up with. But 3 days was an exciting time. I often sit back and think, even with my research that I'm doing now, where would I have gone differently? How would I have planned the Apollo 17 mission differently, knowing what I know now? And I can't figure out how I would plan it differently, other than to have more time and to spend at the places that we actually visited. It was a very, very fine mission. As close to being perfect as you could imagine.
Not long after that mission, about 4 years later, you're elected to the United States Senate from New Mexico. You also served as chairman a little bit later, once your party had control, of the Science, Technology, and Space Subcommittee. What did you focus on during that time in that role?
Focused generally on what NASA was trying to do at the time. Also, the space shuttle was the main focus of NASA. And during that time, the funding was not nearly enough to meet the milestones that had been planned for the shuttle. And we reached a point where the shuttle was just never going to launch because of the buildup of what I called at the time a milestone fence, where problems occurred and you had to delay schedule in order to solve those problems, but it kept building up these milestones out there that you weren't getting through. And so the only way to break through that was to have increased funding. And so I spent a fair amount, one of the things I did, one of many, was spend a fair amount of time trying to persuade the Carter administration to request the supplemental funding necessary to move forward with the space shuttle. It turns out that they just weren't willing to do that until the intervention of Hans Mark, who was then Secretary of the Air Force, came about, and he had a sit-down session with President Carter and convinced Carter correctly that you could not verify one of the nuclear treaties without the space shuttle. And that was because the national security payloads that were reconnaissance payloads that were scheduled to verify that treaty were going to be launched on the Air Force version of the space shuttle. That ultimately did not occur because of one of the accidents, but nevertheless, that was the situation at the time. And so we did get that supplemental that brought us through to the first launch of the space shuttle. I'm very proud of that. Whatever you may think about the policy decision to go forward with the shuttle and not continue to explore the moon, nevertheless, at the time, that was the program, and that's what you needed to have in order to have a continuing national security effort in space. So thank goodness for Hans. He was able to give us the ammunition, finally, to get that supplemental for the space shuttle.
What do you make of the renewed effort to get back to the moon and possibly even to Mars?
Well, I think it's a very important thing. It's something that the nation has to be competitive in space. It's a geopolitical program in my mind, much more so than a scientific program, even though science will benefit greatly from it. The Chinese are our primarily competitor now. It's the Cold War with the Chinese has started. It started probably 20 years ago, but we're just now finally starting to see people recognize that they're our major competitor, and the situation is probably much more serious than it was with the then Soviet Union that stimulated Apollo. So that program needs to go forward. Now, having said that, because they do not have a Saturn V class rocket system to get to the moon, the NASA's had to develop a much more complex architecture in order to land on the moon. And that means that the management risks are higher for actually succeeding. I have every confidence in the young men and women that are actually working the program that Artemis will be successful. But it's going to be a major challenge, an engineering challenge, operational challenge, and a human challenge in order to pull it off. It's an exciting time to be able to do that. But again, it is essential that the United States be successful relative to the broader picture of this Cold War that's developed with China.
As you look back at your service as an astronaut and as an advisor to other astronauts, what are you most proud of from your time serving our country in that way?
I think I just have to be proud of having been involved and being in a position, coincidentally because of my experience and the education, to actually be involved in this period of time. It was a very, very important period for the United States, for democracy, for the continuation of human freedom, and I just feel very grateful that I had a chance to be part of it.